right, you guys, here we are at lesson 1.3. This is our infinite limits and limits at infinity. This first section right here is talking specifically about what about vertical asymptotes. And this section right here is what happens when x is super big. So they're totally different ideas. And so I just want to talk about vertical asymptotes to start. And I'm looking at the pictures before I'm going to try to do anything. And I'm mentioning that I've already said that in the world of calculus, we kind of have these controversies where some teachers will say that this sort of picture means that at whatever this number is, the limit is positive infinity. And whatever number this is right here, if the graph looks like this, we would say that it was going to negative infinity. And that but controversy aside, we all agree that if they are both not coming to the same thing, this side's going to positive infinity, this side's going to negative infinity, that the limit at this number, whatever it is, it will not exist. So we write does not exist. And right here we say that this does not exist either. This side is going to positive infinity, that side is going to negative infinity, so this one does not exist. Okay, so we're just trying to decide which situation we are in when we look at any given function. And so right up here at the top, I have this f of x, and I notice right away that there's an x minus 1 and an x minus 1, which means that I can factor that and find out that if I set that factor equal to 0 and add 1 to both sides, that whole exists at 1. Now it's a removable whole and I have removed it, but that still means that 1 is not in the domain. But this is the part that I don't think is necessarily a review for you. You might not remember it at all. When you are looking at the exponent of a factor, like this factor x minus 2, you set that equal to 0, and you can find out that at 2 there is going to be an even vertical asymptote just because that exponent was even. And then right here at 3, if you set that x minus 4 equal to 0, you find out that there's an asymptote at 4, and we declare it to be odd specifically because the exponent is odd. So you might want to add a note to yourself right here. Look at the exponent for even and oddness, okay? And that's the way to know whether or not, which situation you might be in when you're trying to determine a limit at a particular number. Okay, so let's actually do a couple of problems here. And he says you've seen examples where a limit does not exist at a vertical asymptote. Such non-existent limits can be expressed as infinite limits if the vertical asymptote is even, or if you're just finding a one-sided limit. So I've already shown you some examples of that. Let's deepen our knowledge of that right now. Okay, so the examples below make use of what we've been talking about. And I'll mention that number 4 and number 3 are one-sided limits, so I just moved it up there just so I could do them together because they sort of, they go together, okay? If you take a look at 1 and 2, they also go together. So this one is from the right because I have that little 2 with a plus in the middle and up in the corner, and this is from the left. And so at the end, we could talk about whether or not the limit exists at 2 because we're checking both sides. And remember, you have to check both sides whenever you're concerned that there's some weird behavior going on there. And there's nothing to be factored here, and there's even no parentheses. So how do you know what the exponent is? Well, it's a hidden invisible 1, which means that this function is going to be odd. And so one of these will be a positive infinity and one of them will be a negative infinity. I know that for a fact just because the exponent is odd. So I want to then try to actually find a limit. And it says if I'm coming in from the right, then that's bigger than 2. So I'm going to just try a number that's slightly bigger than 2, like 2.01 plus 3. And I'm going to say I have 2.01 minus 2. And what am I about doing again? I'm evaluating this function at a number that is slightly bigger. So at 2.01, I just want to evaluate the function and see what I get. Now I'm not supposed to use a calculator, and it turns out you don't need one, because what you end up here with on top is 5.01. 3 plus 2.01 is 5.01, and you take away 2 from 2.01 and you end up with a 0.01. And what you guys know about division with, a decimal like 0.01 is all you have to move the decimal over twice. That's all you have to do. So my answer is going to be 5.01. So I'm thinking of a number that's very close to 2. It's 0.01. It's 1/100th of a way from 2. But what if I took it 1,000th of a way? Well, I'm probably going to end up with a slightly bigger number, right? Imagine that I'd add another 0 there. And then if I went to 2.0001, oh, well, you could add another 0. And 2.00001, you could add another 0. I'm telling you that I feel really confident in saying that that's going to be my positive infinity, which means that the other side, I should definitely end up at negative infinity. But again, let's actually try it. So I'm looking from the left, which is a number that is smaller than 2. And so I'm going to take away, I'm going to take away just a little bit from 2, and I'm going to end up at like 1.99. Okay, so f of 1.99, this is me evaluating this function at a slightly smaller number so that I don't run into that weird, division by 0 problem. And so I have 1.99 plus 3, and that is going to be over 1.99 minus 2, and that ends up being 4.99, and this is a 0.01 that I'm dividing by, so my answer is 499. And again, I imagine myself even closer to 2, like 1.99 or 1.999999. I even confuse myself with all the nines, but I know that that is going to go to negative infinity. The problem is right here. Do you see? That's technically negative. And so that means that's technically negative. And now, check it out, I know that that is technically negative. So when you are trying to do like little pieces of arithmetic, especially in a high stakes situation like the calculus exam, the AP exam, you're going to make mistakes, and they just took away your calculator. So you're going to be freaking out. Oh my gosh, I don't have my calculator. So we might want to figure out a method to do this that doesn't involve, using teeny tiny little pieces of numbers with a lot of arithmetic, right? We might just want to start thinking about it in general and paying really close attention to positives and negatives and using that as a tool. Okay, so I showed you the arithmetic so you would understand the basics of what I'm doing. And now I'd like to take a look at these with that concept. Is it going to be positive infinity or is it going to be negative infinity? And is there a way for me to decide whether or not without doing any arithmetic? That's my goal. So I want to know that when I look at this function, and remember these two functions are the same function, and we're just going to look from right here from the right, and here we're going to look from the left, which is weird because they're backwards on the paper. But in any case, and I know that right now I have this, so it's even. It's an even function, and they should both goes to the same number. So both of them, I should either get positive infinity or I should both of them get negative infinity. So can we figure that out? Now, it turns out that in the denominator, if I plug in an actual 1, right, 1 minus 1, and I'm just going to approximate something, right? And I'm not even really saying what I'm approximating because this is kind of shady math. So I'm just like, something is approximately equal to 1 minus 1 and 1 minus 2, and the 1 minus 1 is being squared, but that's just a division by 0, right? But on top, what do I end up with? I end up with a negative number, right? 1 minus 2 is a negative 1. But I'm not even going to write the negative 1 because I'm already doing shady math. Why don't I just say that it's negative? And then here, I'm going to plug in that 0 again. So again, something is approximately equal to what? It's approximately equal to division by 0 on bottom. But what about on top? If I start out with a number that is from the left of 1, let's try something that's like, 1.01. Well, 1.01 would still be a negative number. Do you see that? Because it's still, I mean, anything close to 1, but you take away 2, is still going to be a negative number. So right now, the shady math is over, and I'm going to go back to the original problem, and I'm going to write an answer right next to the question so that my shady math is not going to be something that a grader is going to evaluate, because I haven't made it a part of the actual problem, right? It's just me just sort of writing some random stuff down. They're going to be like, I don't really know what they're writing right there, and they're going to move on. Okay, so you're allowed to write some things down, but don't necessarily make them clear. And in fact, if you don't want anybody looking at it, you can definitely cross it out. Okay, we just want to write momentary things down because we're thinking about something, but then we can just cross it out and say, don't look at it, it didn't mean anything. So now I'm going to say then that my answer for those are both going to be negative. All right, now what if I've been in the mode of doing this for a while? Well, I might accidentally decide that this was odd, right? And then just start trying to decide whether or not, I mean, just literally, if I know it's odd, then I know that the whole limit doesn't exist. And this example's up here for you on purpose. Don't do that, right? Remember to factor first. Okay, so when you remember to factor first, then what you're going to see is you're going to see the limit as x approaches 2, and you see x plus 2 times x minus 2, and that quantity is all over x minus 2. These will factor out, and I no longer have what I think is a vertical asymptote. This is a whole at 2. And remember, x minus 2 equals 0, set that equal to 0 and solve. That whole at 2 is removable. It's not a vertical asymptote. So I can actually calculate that limit, the limit. And here, this is not shady math right now. I said that this was equal to this limit, and now I'm going to say that that limit, right, that limit is equal to 2 plus 2. And so I'm leaving this blank because this question in the grader's mind just automatically goes down. All right, and then I say that 2 plus 2 is equal to 4, and that's my answer. Okay, now this is not likely to be a free response question. It's likely to be a multiple choice question. In fact, all of these questions are likely to be multiple choice questions. So that's why shady math doesn't matter for a while. It's not even something that a grader looks at when you're doing multiple choices. All right, so those are those problems. Now, these we've done some work with this in class, and you do have that cheat sheet that I gave you, but I do want to encourage you to try and not use it, okay? And for those of you who aren't actually in my own class, if you're taking a look at this, it says limits at infinity. If the graph of a function f of x approaches a horizontal asymptote to the left and or the right, f of x is said to have a limit at infinity. If the asymptote is y equals some number, and then the limit of the function as x approaches infinity is approaching that number, in other words, we could say that limits infinity give us n behaviors for graphs of functions. For large values of x, the highest degree terms in the numerator and the denominator dominate the other terms and the only terms that you need to consider. So, when I imagine going to infinity, just like in the above problems, I plugged in a number that was close to my limit. Well, if I'm approaching infinity, a number that would be close to my limit is like, I don't know, like a million. Okay? And you say to yourself, look, if you're going to take a million to the fourth power, well, there's already 6 zeros in a million. And so that's 6 times 4. There's going to be 24 zeros. This term, squaring a million, that's only 12 zeros. And so that number is significantly smaller. So this number right here doesn't matter. And that number, adding a 2 at the end, also doesn't matter. And that 3, none of those things matter. So what matters, the only thing that matters is this right here. And it's like a simplified, an easily simplified fraction. Ready? And again, this is shady math, so you're not actually trying to get a grader to grade any of this. So you're just saying something is approximately equal to, ready? 5x to the fourth over 10x to the fourth can be simplified, ready, into just 1/2. And if you can do that, then you can say, boom, the answer is 1/2. Now, the mystery of why this works is just something that's better gone over in a classroom setting. So we're actually doing this as a review and hoping that you felt good with what we did in class. And if your teacher isn't going over it in class, you might want to review this on YouTube, just random, videos about end behavior. Okay, so then again, that doesn't matter, that doesn't matter, that doesn't matter. I don't care about any of those things. And my shady math says that I can just take a look at the biggest terms. So 5x to the fourth over 10x to the fifth is going to end up being 1/2 over x. Now, it turns out I don't even care that there's a 2 in there. Imagine that you throw a million in there for x, and or shoot, in this case, negative a million in there for x, and what you're going to end up with is 1 over negative really big number, which is negative 0.000000000000000000001, whatever that number is. It is really freaking small. It is basically, ready, 0. It is basically 0. So if you have 1 over a gigantic number, then you're going to get 0. And even if you're on the negative side of the number line, so we think about the number line, here's 1, here's 0, here's negative 1. As I'm approaching from here, like negative 0.000000001, if it's going to 0, then it's still just going to 0. Okay? Now this one right here, again, my shady math says that I have a fraction and I can simplify it. This is x to the fourth and this is 10x cubed. And I want to simplify this fraction, and I'm going to say that I have x over 2. Okay? And it's like, well, if I put in a million and I divide it by 2, then I'm still going to get, a really big number. Sure, it's half of a million. But what if I put in a quadrillion? What's half of a quadrillion? I don't even remember. But it's a really big number. It's basically, ready? Infinity. Now, let's take a look then. What if they make it a little bit harder on us? What if they factored this thing? And I don't know what all of my biggest exponents would be, right? It says make sure that you consider the highest degree terms, not the highest degree factors. So in my mind, again, my shady math right here, I'm going to say I have a 2x times, ready, an x squared. Do you see it? Because if I expand that, I will get an x squared. Then on bottom, I'm going to say that I have an x times, ready, a 3x squared. And altogether, that is going to, okay, remember, hold on though, this is 3x being squared. Be very careful there. I almost made a mistake. 3x is being squared. So what I end up with on top is a 2x cubed, and on bottom, what I end up with is a 9x cubed, because 3 also is squared. It is inside of these parentheses. And now that I notice that the exponents match, I could say then straight up that my answer is 2/9. Okay, that is cool. Now, make sure you consider we have done that. And I want to take a look at these next ones. Okay, it says rational functions like those above have at most one horizontal asymptote. So the limit is the same whether x approaches infinity or negative infinity. However, radical functions frequently will have 2 horizontal asymptotes. So we're supposed to find these limits, okay? And they look scary, but this is again one of those things where I'm trying to get everybody in the room to just have a few extra problems that they've like, oh, I remember that. When you do the AP exam, you're looking in the multiple choice. So this is just one multiple choice question here. And if you learn it, great. You could get that 5 on the AP exam. But if you don't learn it, it's probably not going to keep you from, from passing. If you have the strength of your learning in other ways, you could pass this test without knowing this one problem. But basically, do you see how if I try to plug in infinity here, my mind just starts getting confused, because there's an x squared and then there's a square root around it. And so again, my shady math says that I might like, instead of trying to plug in some infinities here, I might actually just like to just imagine 4x squared being taken the square root of, because I know that 4 is a squared number and I know what the square root of x squared is. So I'm going to say shady math tells me that this is really 2x. Now on bottom I had x and I still have x, so I'm going to say then that my answer simplifies to a 2, and I'm just going to throw that in right here. Okay, now the next version, again, I mean, you could tell this is the same equation, and he's like, but what if I was asking you what happens when you go to a negative infinity? Well, when I go to negative infinity, I'm still thinking about, it like this, as the square root. Shady math says that the square root of 4x squared, it does simplify, but here's the thing. What you need to know is that over here, when I was just dealing with all positives, I wasn't worried about the possibility that it's negative. Right now, I want to worry about that. I want to think about what if it was negative? And here's what I want to do. I want to say that it would not be negative anymore. Because if I throw in a negative a million up there at the top, then what I'm going to do is I'm going to square it. Okay, I square it, it becomes positive, then I take the square root of it. So I'm guaranteed for that number on top to be positive. And on bottom, I'm not squaring anything and I'm not taking the square root of anything. So that number on bottom is guaranteed to be negative. And so that's when I say that I have, ready, negative 2. Now, this is one where you really might want to pause and take a look at this graph, as it's kind of a fun graph to look at and you could see what's going on when you take a look at it, all right? So then I want to talk about these exponential functions as well. And I remember that the basics of an exponential function, you have the two scenarios. And, I don't even really want to draw the x-axis because, things can shift up or they could shift down, right? But basically, I have this version of an exponential function, which is a growth, right? Where I have growth. And then I have the other version of exponential functions where I have decay. And so I just want to try and take a look at these limits with that idea. And I want to say that the growth equation is something that looks like this, y equals e to the x. And the decay function is something like more like where e to the x is a number greater than 1. Let's try this, where I say that, how about I do b to the x, where b is greater than 1. On the decay side, I want to actually say that it's y equals b to the x, but here b is going to be between 0 and 1, meaning that it's less than 1. So it's like a half, it's a quarter, it's a third, it's 0.99 all the way down to 0.01. Okay, so now let's take a look at this guy and say, well, what about just regular e to the x? Because I just was talking about it, that e to the x grows like this. So when I'm approaching negative infinity, I remember that there's a horizontal asymptote, and that guy is at 0. But that's just from memory, So I'm hoping that we're going to go over exponential functions deeper, not this week, but next week. So we'll explain a little bit more about things to remember for e to the x. This is like an introduction to that for us. So taking a look then at the other direction, this, by the way, is the direction where x is heading towards negative infinity. Let me write that better. X is heading towards negative infinity. And right here, this is where x is headed towards positive infinity. We already noticed that x was going to be going bigger, so that e to the x would definitely be getting bigger. But this next one is much, much more complicated. Okay, so let's do a little bit of algebra on this. I'm going to say, and these are called the properties of limits that I'm about to use. You maybe haven't seen it before, and so I'm glad to show it to you. Ready? The properties of limits say that if I have a function that has two pieces to it, that you can break each limit up and you can look at it individually. So here is e to the negative x. That's one limit that I want to calculate. And then there's another limit that I want to calculate where x is heading to the same number, but it's just the rest of that graph. And then what I'm going to do is I'm going to add those two limits together at the end. Okay, so I definitely want to get to that. So e to the negative x is the same thing as 1 over e to the x, which means that as e to the x gets bigger and bigger and bigger, because we know that, you multiply e time to the power of 10, that's e times e times e times e times e. That's a really big number, right? So again, I have this thing where I'm dividing by a really giant number, and this is me shady math. I'm thinking about 1 over e to the x. I know that what this is tending towards is going to be 0. And so I don't have to worry about, that limit. It ended up being 0. This limit is a lot more easy to calculate because I don't care about any of that. I only care about the first big two terms with their exponents that are turns out 2x squared over over x squared. That quite easily cancels out, and then I end up with a 2. So I'm just going to come up here and I'm going to say my final answer is 2. All right. Now, what if, let's take a look at 18. It's slightly different, isn't it? Okay. And when you're looking at it being slightly different, you're like, well, what do I matchy with? I've been sort of picking like the first two terms that have the highest degree. And you might be tempted to say, well, these things match and I should set them equal to each other. But it turns out that realistically, again, e to the x becomes so big so fast that you'll find out that that's your biggest. It's absolutely bigger than that guy. So now I don't care about either of those pieces. My shady math says that my answer is going to be 2x squared over e to the x. And I'm imagining what happens as that goes to infinity. And so I'm going to say that I know on top I'm going to get a positive number because I'm going to square it. Okay, I'm going to square it, so it's going to be positive. And obviously, if you throw in a million and you square it, you're definitely getting a positive giant number. And then you multiply that by 2, but whatever, it's still a giant number. And in the bottom, I already knew that I was getting bigger. And so I say, oh wait, sorry. E to the x, though, it's even bigger. It's bigger than this number right here. Whatever this number is, it's never going to be as big, right? Squaring a million is never going to be as big as taking e to the millionth power. So what do I have? I have a small number over a big number. Again, just like I did over here, this is a small number over a big number. And I'm going to say that that answer, ready, is 0. Now remember, if you are trying to work through a problem on free response, you use some shady math, you do actually have to go back and restate the original question with your answer in order to get some points. All right, so that's why I'm always making sure that I put my answer right up here at the top, and my equal signs are real equal signs. And I'm trying everywhere that I'm doing shady math to have approximation symbols. So please go back and double check your work whenever you're doing sort of shady business. All right. And there you go.